believe it's also going to change and reshape EDA. So we quickly go through, let's get started. We quickly go through the industry trends. We'll talk about key challenges that we see, and with every challenge it comes with opportunity, and then we'll talk about opportunities as well. On industry trends, we'll definitely start with looking at AI models, which is a cornerstone of AI. Without understanding trends in the AI model where it's going, it's very hard to talk about the rest. And we'll talk about three major vectors: compute, memory, and internet. And naturally, when we talk about AI, we cannot not to talk about power. It is a very critical aspect. So let's get started probably. And again, AI model, you can see that size of them evolving very, very rapidly. It's growing. But what is important to highlight is that it's not just sheer number of parameters. I think the industry moving from monolithic dense model, it's already moved probably, I would say, to models that are more reasoning-centric, agentic system, and running on memory and interconnect-bounded infrastructure. What is important than just share of floats, shared computing is not enough. As we move and we support spaces like MOE, for example, it's very critical not just have floats, but also have adequate memory bandwidth as well as interconnect. And you can see even from the chart how rapidly growing the number of parameters, while it's still focused right now shifting how to use this efficiently, not just, hey, go the more the better. It's really how you grow, but you want to get efficiency more out of the same number of parameters. So let's look at the three vectors that we were talking about: compute, memory, and interconnect. So if you look right now on compute, so if you look at frontier models, training compute is scaling enormously. From my point of view, roughly 4.5x per year. And if you look at shared amount of global AI compute capacity is expanding on unprecedented rate. And you can see that it grew more than 30 years since in the last 5 years, something like that. This is unprecedented, and naturally compute is a very critical that we need to be looking when we are building AI accelerator. But it is not enough, as we mentioned. And memory bandwidth is becoming more and more fundamental right now. It's not like memory bandwidth is not increasing. It is also increasing 1 bit, and you can see it's increased 10x over the last 5-6 years. But if you compare to compute, it's definitely lagging behind. Compute scaling about 3 years. And if you look at the chart, you can see the gap between compute and memory bandwidth is widening. And this is what people call memory wall, and you can see based on the memory prices and the stock price of some of the memory vendors is clearly reflected. And what right now, if you see the performance of some accelerator and that they are running workloads is actually limited by memory bandwidth, not by compute. And this is very important to understand because we need to compare more compute in AI accelerator. It doesn't necessarily mean more performance. Let's look also on the next important component is interconnector. And mixture of express MOE is pretty much mainstream right now. If you look at all key models, they all use MOE. And it naturally demands higher network bandwidth. And you can see here a chart to show how recently network bandwidth scaling as well, you can see very exponentially. And in what you see here, it is important pretty much three vectors that needs to be balanced. And sometimes you are prioritizing interconnect over compute or memory bandwidth over compute. You need to have balanced system in order to achieve the best performance. And this will play a critical role when we'll talk about this later. And last but not least, power. You cannot talk about AI without talking about power. And it is right now probably dominant deployment constraint. And here when we are talking about optimizing AI accelerator or anything, we are not talking about optimizing peak performance. To some extent, it's not even a matrix. When we are looking at optimizing, it's usually optimizing performance per dollar or performance per watt, and to be frank, they correlate pretty well with the capacity. And the more power you get, and you can see chart how power is scaling, it's not just power consumption, it's actually generate a lot of thermal challenges that also drive additional cost and performance, and some of the workload might be just even limited. Trend, you will see that it's very limited by thermal constraints. And another important point here to highlight that it needs to be optimized at the system level, not just at the chip level. This is very critical item to highlight. And if you look today, pretty much AI accelerator have crossed a threshold where the hardest problem no longer live inside the chip, they live at the system boundary. This is where, because as a standalone chip itself, it's not very beneficial for AI because very few things you can run on single chip. You really need to look at the system level. And if you look at the history of ADA tools when they started, I don't know, 30 years ago, 50 years ago, I don't know for sure, you can check it. It's naturally, ADA tools were designed to design chips, not a chip. And this is where I think we'll talk about more what challenges we are facing because of this. And as a result of this, what are the opportunities? Because I believe that this will need to drive a lot of innovation in the industry next year. So let's look at the key challenges. And again here, we'll go through several vectors and talk about them. And naturally, some of them are pure silicon design, some of you will see it's accelerator. It means it needs to be worked closely with software. This is absolutely critical. Now, all these challenges, as you can see, of the design team that deal with AI accelerator design needs to tackle these challenges one way or another, more efficiently or less efficiently, but they're tackling them with homegrown tools, capability, Excel file, various models, whoever figure out the best way. Okay? So let's probably get started. And this is what we talk about, right? So if you look at the AI, it's behaving as a distributed system. And with a lot of chips connected and data going back and forth between multiple chips. And today, a lot of risk emerge at the boundaries of compute, memory, interconnect, and software boundaries. As we discussed, EDA abstractions stop at this boundary, usually use it in different pockets. But how it's all coming, working together, it's pretty much today EDA capabilities are limited processing. And most of the cases, EDA tools and capability allow you to do local optimizations of different pieces, but as an AI system, it succeeds or fails globally. Even if it's one piece is not optimized, it's not working well, it's not optimized, the whole system will not be optimized because this will become a major bottleneck. So this is very key message that right now, how we are going to start crossing all this boundary, what are the capabilities we have. Today, a lot of them are, I would say, sort of homegrown capabilities that different companies develop. And and also relying on experience of the people. Another one, verification cost. So, various reasons verification cost is exploding. You can see right now that today verification cost is about consumed, based on estimation, about 70% of the total design, of the total effort. And you can see, similar to what we call memory wall, gap between design effort and verification effort is also increasing. It's a lot of different reasons. Data design size is growing, a lot of data traffic, fabrics regression consuming disproportional amount of data, resources, and so on. This is another challenge. AI tools, yes, there are AI tools that help you to mitigate it, but to be frank, I think we are only getting on this path. And right now, from my perspective, ROI is remains to be relatively limited. I think there is a significant opportunity ahead of here to get it better. Okay, but this is, and we'll talk a little bit more about this in opportunities part. But this is another important vector that we need to consider. Another one that usually people don't pay much attention is infrastructure. Because amount of compute, I will show you some chart later, is significantly increasing. So pretty much a lot of cases productivity of people, EDA productivity is gated not by feature A or feature B. It's how much, what compute infrastructure, what is your scheduling, and so on and so on. And you can see chart here again, it's not exact science, it's estimation, but you can see how significantly changing amount of time, amount of focus and attention you need to spend on compute infrastructure. And from my point of view, I think EDA capability become more cloud aware. I think pretty soon we will hit some ceiling because it needs to be more cloud aware in order to achieve the best performance and needing and optimizing conditions. AI and EDA. Now, I know there is a lot of AI capabilities there, and it's evolving, and I will tell it from my experience, if I compare a year ago, 2 years ago, there is significant improvement. But I still believe we are just scratching the surface. There is still much more that can be done. If you look today, what most of AI capabilities are doing, I'm just trying to summarize, it's improved tool ergonomics, it helps you to find the bug problem easier, it helps with local optimization, but it doesn't significantly change higher level design outcome. Higher level design outcome, it still mostly depends on designer, on engineers, on their expertise and knowledge. So I think pretty much, it doesn't help with system level design. And I think this is another sort of, we can call it challenge that potentially can and should be overcome. Power efficiency gap, and this is probably one area where I am super passionate about. And every time I talk about this, when I look at the amount of power current AI accelerator consume, data center consume, it's mind-boggling to me. But again, it's not about, just want to reiterate, peak performance. It's about performance per watt, how many tokens per watt, which is very closely correlated to tokens per dollar or performance per dollar you can generate. And it's not about how fast transist, a significant amount of energy goes into data movement, unlike regular. And data movement is definitely within the chip, if you look at breakdown, but if you also look at data movement, how much it's consumed. It's between chips. And if you look at the current EDA tools and flows, they're super good at convergent timing, but unfortunately it's not easy to figure out, to show where power goes by workload. And again, this is AI accelerator, it means workload, right? And without workload-aware power modeling, power closure pretty much becoming late-stage firefighting or optimization if you missed it at earlier phase. And the way you missed it is based on experience or whatever capability you developed at times. And this is a key challenge because it's driving a lot of things, and you saw we discussed it previously, of how much power right now being consumed in the world and how much is growing consumed by AI workload. Last but absolutely not least, software and LLM model requirements. So the whole AI accelerator is built to accelerate software workload and how to make them work faster. Okay? And the whole idea here is, hey, can we co-develop, or some people call it vertical integrate, hardware and software. So by changing hardware, by changing software, mutually we will achieve the most efficient route. But in order to really achieve it, you really need to have significant chip length and have very early base silicon platform or analysis capability that will allow you to do this analysis, experiment, and figure out what is the right architecture of the hardware and architecture of the software. It comes together. And today, again, company do it in-house with whatever different company do it differently, different teams are doing it differently. But this is another, in my view, future opportunities, how to enable hardware software co-development that is missing. So now let's talk a little bit more about EDA opportunities. Every challenge comes with EDA with opportunities. It's by definition, and now we'll talk about this opportunity. Now, I already mentioned that, hey, one way or another, every company decides do this, figure out some in-house capability, what to do, how to do it, and does it better or worse, but it does. Now, you can ask, hey, what is the problem? Why you need to change anything in the data? Why you can't implement it? And here's what I would draw some analogy, and you can probably guess that I've been in this industry long enough. If you go back really, really long time, when I only started my career, so it's really long time ago, I remember a lot of companies, semiconductor companies, that have own CAD division, that develop EDA tools and capability. It looks weird, but I can tell you a lot of companies have their own in-house lessons and routing tools that probably today is unheard of, right? So I think this is how I view it as the next wave of evolution. Then over time, it's not going to happen overnight. But over time, I think this is the opportunity for EDA industry to evolve and develop these capabilities that eventually will become default of them. Similar like placement and routing capability involved many years. So let's probably start talking a little bit about system-centric EDA, and we roughly touch about this. Okay? So data movement is very critical. How to minimize it, what to do. It's not just about logic inside the chip. Workload behavior and system bottlenecks. How does it work? Is it memory my bottleneck? Is it interconnect my bottleneck? How should I prioritize resources in the system? It's not just about closing the timing inside the chip.
I can have super good timing and sization. Chip will perform perfectly. But if my interconnect becoming a bottleneck, it's waste. This is important to understand. Now, we also need to look at end-to-end system setup, because when we are doing it, besides AI accelerators, there is a lot of other components. There is speeches and so on, that needs to be taken into account. Full stack thermal optimization becoming super critical, and let me sort of give some example and idea, right? We all know here we need to extract heat, let's build as fast as much as possible, cold plate and so on. But now, in general, we need to look at across the step all the way from transistor to data center, because heat needs to go somewhere, right? And if you, for example, liquid temperatures, you're forcing liquid temperature to be very low because you want to extract maximum amount of heat from the chip, it's not coming for free. Somebody needs to pay for it and make what's the right balance, right? Maybe I will slightly reduce frequency performance of the chip, but it will allow me significantly, not significantly, but will allow me increase temperature of the liquid cooling and find this sweet spot that giving me the best performance per dollar or performance per watt. You need to analyze it across the board. Let's look at the same example of power delivery. And you know right now power delivery with all the power that's being consumed is very critical. But let's look from the time when cable getting into data center until it gets to the transistor. It goes through many different transformations, and every transformation you're losing some power by definition. And at every stage you assume worst case scenario and you do allocate power based on the worst case scenario, which is probably worst. At the end you will waste a lot of power. So what is a realistic scenario? How realistic workload will work? And this is all opportunity to discuss so we can optimize it and plan for not worst scenarios that will never happen, but plan for more realistic scenario. As a result of this, we will optimize solution. This today, is it done today? Is analysis done? Yes. There are Excel files, there are different models, different companies are using it, but it's mostly in-house. Another one, let's look at AI-driven design space exploration. Today, as I mentioned, for example, we would like to navigate through massive design spaces, look at different options, what is the memory hierarchy, what is the interconnect topology, what is power performance rate. Today, this capability are missing. It's usually based on, there is some design capability, whatever in-house and people experience. But in terms of do we have sort of AI-driven design space exploration system, I'm not aware of this. Okay? And idea here, if we could develop capabilities that can faster iteration and early architectural feedback, it would be really beneficial because this is at this stage you can do the maximum impact to the efficiency of the system and what you are doing. Another one, pretty much, idea is if we can make AI to help us to decide what to build, not just how to build it faster. I know it's a big ask. I know it's not going to happen tomorrow, maybe not even day after tomorrow, but this is definitely a opportunity. If we can explore various options across system configuration, different resource trade-off between compute, memory, interconnect, memory hierarchy, pick and take, whatever you want, what is the best option? I think eventually we will go from local optimums to global options that will give us much better results. Cloud native EDA. So this is we already touched recently. So if you look today, and again, this is not exact because the data is very difficult to get, it's pretty confidential, but on average, you can estimate that from 2016 to 2030, CPU hours consumed for tape out, it's went up by 20 to 30x, whatever you can estimate. It's a huge number. Now, what is driving design size? Of course, it's growing rapidly. Process technology getting more complex and so on. It's also consume more resources. Multi-chiplet approach, it's contributing. You need pretty much, it's not one tape out. If you have two chiplets, it's two tape outs. And now you all know there is more than two chiplets. Plus, if you add interposer, it's another one, and so on and so on. So if you add everything together, it's a normal increase in compute resources that require for tape out. Okay? And I think if we continue at this pace, at some point in time, compute resources, compute will determine what flows are feasible to run and what flows are not feasible to run. Because it just becoming not practical unless really controlled. And this is why I think EDA capability is very critical when I call cloud native EDA also to be aware of the cost and capacity and be able to integrate with a cloud scheduling element. Because even right now, I can tell you that you try to do certain modeling, when you calculate how much resources you need, it just becomes in some cases unrealistic. Okay? And this is a very important item. I know in the past, for example, I also was in design team. I never cared about computer resources, it will happen, it will come. I think we need to get to the point where we start looking at it in order to execute. Verification intelligence. And we talk about this at how much, by the way, if you look at compute, significant portion goes to verification. It's not just the physical design of everything. Okay? So, key is decide what not to run. And you could probably tell me, hey, there are a bunch of AI capabilities, AI tools that will tell you test selection and so on. Yes, there are. From our experience, it's limited value. I think there is more work that needs to be done. But specifically, we need to focus on test prioritization, coverage-driven improvement. Another important aspect, of course, I think they need to develop hybrid strategies for verification, encompassing formal simulation and simulator and prototyping capability. Hybrid. You cannot go one way or another because it's becoming non-sustainable. And I will talk, for example, if I right now will try to build, first of all, you cannot even build simulation model AI accelerator itself. It's not even feasible. Even if I try to build the AI model of the entire emulation or prototyping model, it's also becoming enormous. So this hybrid strategy, in my view, is becoming a must, and it needs to be developed. Again, with other cases, a design team find a way how to deal with this, how to work around it, but it would be great if we'll have some more uniform and standard way to approach it. Yeah. And pretty much, I think idea here request is let's make verification selective, data-driven, and powerful. Okay? Because at this point in time, I don't think we can continue scaling in the traditional way brute force approach. Because I think it will hit the limit very, very soon, if not already. Power modeling and optimization, we talk about this. And key here is to optimize hardware and software for power efficiency. Again, the objective here is what to optimize or not, and we need to bring workload aware energy modeling in all exploration. Even during architecture phases, for sure, later on. And like any design work, we need to enable it faster iteration at early phase. Because if you come late in the project design cycle, not much you can do. You can pick here, there, but major decisions on that. I don't think today, at least I'm not aware of early models, standard infrastructure or capabilities that allow you to build this model. Every team builds their own model and based on it. Now, let's a little bit, I want to spend a little bit more time on software and LLM modeling and so on. And I think idea here we talk about how you can bring all this AI workload modeling and analysis as early as design phases as possible. All the way when you only select an IP or exploring architecture. Today, as always I mentioned, it is done through Excel file and so on. But even on later phase, if I try to develop, try to work silicon today, if I look at the platform, what we have today, simulation, which is super slow, and there is limited capacity. If you look at emulation capabilities, it's better, it's faster, but it's also with the new sizes of the accelerators that's coming. It's already almost, it's impossible to fit one full accelerator, so you need to go with a reduced model and play different structure. If I look at the system level, it's pretty much you need to innovate and come up with how you want to model it, and most likely it will be something extrapolation from the exactly model, or you develop some type of house. Okay? So idea is that can we build capabilities that will allow us to get software and LLM modeling only in design cycle. As design getting mature, the same model will get more refined, but it's not just for hardware, but also so software folks can also iterate and figure out what is the best solution. Because this is software hardware for development, in my view, it's a unique path that will get us to the best possible. So, if I look at what are the key takeaways, so, and we discuss, system focus is required. Focusing exclusively on the chip design is not sufficient at all. Okay, and this is a key factor, and when we are talking about system focus, just want to maybe reiterate. We need to look at how the whole system going to work, which is include various SoCs, chips, which is not just AI accelerators, there are also switches and so on. But we also need to keep in mind how it's going to work for software and model various aspects, power delivery, thermal, and so on. So this is a huge scope, how we do it. Okay? Second important item, scalable silicon platform, because this is a critical to evaluate workload and polyphases and also keep refining. Today this is very, very expensive, and in some cases you cannot even go to full scale. So you need to find solution with some hybrid methodology or something like this that will allow you to achieve these results. And AI-driven exploration can help you make better architectural decisions earlier. Again, today majority of architectural decisions come from people experience, people idea, and whatever analysis and in-house models they have. In summary, what I would love to see, next generation ADA capabilities should enable better system level decision earlier through AI and hardware software co-design. This is, in my view, hardware software co-design for AI is absolutely wonderful. Thank you very much, everybody. We have maybe